let's look at a concave spherical mirror. Now, for concave, there's a difference between concave and convex. For a concave mirror, if you look at imagine a basketball. Now, cut a portion out of the basketball and take that cut portion out and illuminize the inside surface. Okay, that would be the concave part of the mirror. The outside of it would be the convex part if you illuminize the outside. Now, it's spherical because it's a part of a sphere. So if you look at this curvature here, this is the concave curvature. If you imagine this as being a sphere and continue it on and also continue it out and in that way, this is a mirror that is literally spherical, but it's a portion of a sphere. The sphere is going to have a center, and we'll label that C. And in between the center and the surface, we call that the focal point. Okay, that's where the focal point is located. Now, let's say that an object is located beyond C, and we're going to draw an arrow to represent the object. If we have an arrow on this is the axis, and we're just imagining that that part of the mirror can't be seen, and this is on the floor arching up like that, and it's part of a concave spherical mirror. This is the object, and we basically have two ray tracing rules that we're going to work with right now. If an image is going to be formed, the object is located here, the incident ray of light is going to come in parallel to the axis. If it comes in parallel to the axis, it's going to reflect, according to the law of reflection, at an angle equal to the angle of incidence. But this is a curved surface, and that reflection, the reflected ray, actually passes through the focal point. Okay, so the rule is basically this. If a beam of light comes in parallel to the primary axis, it's going to reflect off the surface of the mirror and pass through the focal point. It still obeys the law of reflection because that's a curved surface, not a flat surface. The normal would be drawn here, and theta 1 is still equal to theta 2. Now, the second rule is if a beam of light or a ray of light passes through the focal point, it comes out parallel. Now, where those two beams of light cross is where the image is actually going to show up. Now, for a concave spherical mirror, that image is going to be smaller. It's going to be upside down. It's going to be located in between the center and the focal point, and it's going to be a real image. Okay? It's going to be a real image because it doesn't appear to be inside of the mirror like we talked about the flat mirror. So just recapping real quick. If an object is located beyond C, the image is going to appear smaller, upside down, real, and in between C and F. All right, now let's move the object to the center point. I'm going to erase this for space and draw this here. That's the axis, concave spherical mirror. Draw the center point here. Draw the focal point in between the surface of the mirror and the center. Now the object is going to be located at the center. Using the two ray tracing rules. If an incident beam of light strikes the surface of the mirror and it is parallel to the primary axis, it's going to pass through the focal point. If a beam of light passes through the focal point, it's going to come out parallel to the primary axis. And the image is going to be directly underneath the center. It's going to be the same size as the object. It's going to be upside down and real. So I'll write those down. The image is going to be the same size as the object. It's going to be upside down. It's going to be real, and it's going to be located at C. Now let's take that object and move it in between the center point and the focal point. So we redraw the diagram, put the center here, put the focal point here, draw the object in between the center and the focal point, and use the two ray tracing rules. Any beam of light that comes in parallel with the primary axis is going to leave out through the focal point, and any beam of light that comes out through the focal point is going to leave parallel to the primary axis. The image is going to be located beyond C. It's still going to be upside down. It's going to be larger, and it's going to be real. So it's going to be located beyond C. It's going to be larger. It's going to be upside down. It's going to be real. All right, now let's move the object at the focal point. And the next two are kind of complicated, so bear with me here. This is the center point. This is the focal point. The object is going to be at the focal point. Any beam of light going parallel to the primary axis is going to go through the focal point. Now, we cannot have a beam of light that passes through the focal point because the object is standing on the focal point. We have a third rule that we haven't addressed in any of these, but we can go back and look at that later. Any beam of light that comes in and passes through the center point reflects back on the center point. And if you look at, let's continue on and say that a beam of light comes in and hits here, and it actually strikes the object. If a beam of light strikes the object and it reflects off of here, it's going to leave with the following the law of reflection at an angle. All of these beams of light will leave, and as they leave, they're going to be parallel. So if an object is at the focal point, all of the beams of light actually leave the surface of the mirror parallel, so the ray traces, they never cross. The beams of light never cross. That means that if an object is located at the focal point, it won't have an image, either a real image out here or even a virtual image that appears inside of the mirror. All right, now let's look at if the object is located in between the focal point and the surface of the mirror. I'm just going to erase these two here. All right, well, so for this one, there is no image. And that's for an object located at the focal point. Now, for a concave spherical mirror, here's the center and the focal point. If the object is located in between the focal point and the surface of the mirror, the image is going to be virtual. Now, this is interesting because a concave spherical mirror can form both real and virtual images, and no image at all if it's at the focal point. So, to ray trace this, any beam of light that passes through the focal point kind of goes up, and the object is going to come out parallel, and any beam of light that comes in parallel passes through the focal point, but we're just going to draw that much. We're more concerned with the virtual part of the image. So if we draw the axis going in, this is the reflected beam. We're going to ray trace that back, and this is the reflected beam. We're going to ray trace that back. The virtual image will appear larger than the real image, and it's going to appear into the mirror, and you draw the dotted lines from the reflected rays as if they're coming from inside of the mirror out and from inside of the mirror out. The image is going to appear right here it's going to be right side up. Okay? It's going to be right side up. It's going to be larger, and it's going to be virtual. So a concave spherical mirror can form real images if the object is located beyond C, at C, in between C and F. It's going to form no image at all if it's at the focal point, and it forms virtual images if it's in between the focal point and the surface of the mirror.